Continuing along with our discussion of three-dimensional graphing, today we're going to be looking at how to find where the midpoint is between 2 points in space. And by space I mean as opposed to on a two-dimensional coordinate plane, three-dimensionally in space. So how to find the midpoint between, say, here and here, and how to find the distance between 2 points, such as the distance from here to here. So we'll start with midpoint because that's, I think, easier. So the midpoint between P and Q would be halfway across this segment. Let's see. So sort of diagonally inside that prism is a segment, and halfway across that segment would be the midpoint of that segment PQ. Zoom in a little bit here. So where is that located? And really all we need to think about is the fact that that point's going to be halfway between the x's, y's, and z's on these 2 points. So halfway between the front and backness of the points, halfway between the left and right distance between those points, and halfway between the vertical distance between those 2 points. That being said, this formula should look pretty familiar. We already have a midpoint formula on a coordinate plane where we average the x's and average the y's. So three-dimensionally, we just have to account for the fact that we want to average the z coordinates as well. So that's the midpoint formula in space, a three-dimensional midpoint formula. So why don't you try these two. Let me zoom out a little bit. And you can hit the pause button, and using that formula, see if you can find where the midpoint is on each of these 2 segments. Alright, let's see how you did. So for the first one, the midpoint of segment PF, if I average these x values and average the y's and average the z's, it would look like this. Notice there's just one set of parentheses. I average my x's, add them up, divide by 2, average the y's, average the z's. So I'm just using that formula to get halfway between, again, the left-right, the up-down, and the front-back distances. So -3, -4, -5 is the answer. And the other one, you can pause the video if you need to look at it more closely, but the correct answer is -2.7, -5.5. And again, notice parentheses with the commas, not only in the answer, but also in the work. Now that first one, this pair of coordinates actually was this picture. So our answer was -3, -4, 5. So let's plot that point and see if it appears to be right. -3, -4, 5. I'm going to zoom in a little bit again here. So -3, -4, 5 would be -3 for x means go back 3 tick marks on the x-axis. -4 for the y means 4 spaces to the left. 1, 2, 3, 4. And 5 for z means up 5. 1, 2, 3, 4, 5. So right there is where we got our calculations to show us where the midpoint is, and that does look right. So that's halfway between those vertices. So that's the midpoint formula in space. Much trickier to prove, but more interesting maybe, is the distance formula in space. How would we find the distance between these points? So to start, I actually want to go back a little bit and remind everybody about where our two-dimensional distance formula comes from. If I wanted to find the distance between A and B, you know, we have the square root of x2 minus x1 squared plus y2 minus y1 squared. I want to remind everybody where that comes from. That comes from the Pythagorean theorem. If I want to know the distance between these 2 points, I could always draw a right triangle. And I could do the Pythagorean theorem, because I can calculate how long the 2 legs are. This leg, if I count, is 1, 2, 3, 4, 5, 6, 7 spaces over, but I don't really need to count. It's just the distance, the positive distance between -3 and 4, the x values. -3 is the distance to the left, 4 is the distance to the right of the origin. So this length here is, I know it's 7, but it's really this minus that. That's why it's 7. 4 minus -3. Same thing for this vertical segment. Sure, I can count 1, 2, and I can see it's 3 spaces high. But I could also say that it's point B has a height of 2. Point A has a height of -1. So the difference between them is 2 minus -1. And again, I know that's 3. I know this is 7. So the Pythagorean theorem would tell me how long this is. If I do 3 squared plus 7 squared equals c squared, I can solve and get it. So if we do that same thing more generally over here, we're going to actually derive the distance formula. If I want to know the distance from C to D, I could think about drawing a horizontal and a vertical segment, which would be perpendicular to each other. The length of this segment is that x value minus that x value, just like it was over here. 4 minus that -3 is that 7. Same thing here. So this bottom side is x2 minus x1. That's the length of that segment. The length of this segment is y2 minus y1. This y value minus that y value. So if I didn't know the distance formula, the Pythagorean theorem would still allow me to figure out how long that red segment is, the distance from C to D. The distance from C to D, let me zoom out a bit. Distance from C to D is going to be, according to the Pythagorean theorem, if I do a squared plus b squared equals c squared. This is one of my legs, so this length squared plus this is my other leg, so that length squared is going to equal my hypotenuse, the distance from C to D squared. Leg square plus leg square is hypotenuse squared. And since I'm trying to figure out how long it is from C to D, the length of that red segment, I have to get rid of that square with the inverse operation of square rooting. So the square root of CD squared is CD. And what is it? Well, it's this. So the distance from C to D is the square root of x2 minus x1 squared plus y2 minus y1 squared. That's our distance formula. That's where it comes from. But that's our two-dimensional distance formula. What we're trying to do now is come up with a three-dimensional distance formula. How to find the distance from A to B now if we think three-dimensionally. And instead of just drawing a right triangle, what we could always do with 2 points in space with different x, y, and z values is we could construct a right rectangular prism and put A and B at opposite vertices. So we're wondering how long is it diagonally through this box? What's the distance from A to B? Now if this is a right rectangular prism, that means all these surfaces have 4 right angles. I'm going to start by drawing that segment, which is meant to look like it's going across the bottom of the prism. So your eyes might be playing tricks on you a little bit, and kind of one of those optical illusions where the figure moves around. But we're looking at the bottom of the bottom rectangle, and I just drew a diagonal. And I want to figure out how long this is? For starters. Well, this is the distance from here to here. So where is this point? This point is just below this one. So that means the only difference is going to be the z value. This point has the same x value, the same front backness as b, so it's going to be x2. It has the same y value, it's no further left or right from b, so it's y2. But it has a different z value, but it actually has the same z value, which remember is the vertical distance, as a. It's on the same bottom plane of this prism as a, so z1. And if we compare these points and we see that they have the same z value, then we can figure out how long this is with our two-dimensional distance formula that we just proved. The distance from A to C is the distance formula. It's the square root of x2 minus x1 squared. Oops. x2 minus x1 squared. I'm writing with my arms wrapped around a tripod here. Plus y2 minus y1 squared. So that's how long this segment is. Remember, our goal is to figure out how long it is from A to B. Do we know how long this is? Well, definitely. They have the same x values, they have the same y values, their only difference is their z values. So this length is just going to be the difference between z2 and z1. Now there's one more segment to draw, and this is all going to come together nicely. And what I want you to try to see in this picture is a right triangle diagonally sitting inside this prism. I'm going to shade it so we get a better view of it. This right triangle is the one we're going to use to figure out our three-dimensional distance formula. We know how long this leg is. We know how long this leg is. Pythagorean theorem will tell us how long this is. And whatever it comes out to be is our distance formula in space. So we'll zoom out a bit. So I'm going to write out the distance formula using, let's see, the hypotenuse squared. So AB squared, so that's like C squared in our Pythagorean theorem, is going to equal this leg squared plus this leg squared. So let's start with this one. That entire number, the square root of x2 minus x1 squared plus y2 minus y1 squared. So there's one of the legs of my red right triangle. So that's one leg squared plus the other leg, which is this one here, z2 minus z1 squared. So leg squared plus leg squared equals hypotenuse squared. All right, well, for starters, this radical and this square are inverse operations. This means we can rewrite all of this as AB squared equals, again, that radical and that square are undoing each other, so whatever's inside comes out, just x2 minus x1 squared plus y2 minus y1 squared. And over here I've got a z2 minus z1 squared. And if I want to know what AB is, the distance between my original 2 points, I just have to get rid of that square by taking the square root of both sides. And here it is, the distance between those points has to be, and doesn't this work out nicely, the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. That was a lot of work to get there, but I don't like just giving you formulas without explaining where they come from. That is the distance formula in space. So the good news is, like the midpoint formula in space, it's very similar to the two-dimensional version. We're just adding this extra term here to account for the 3 dimensions. So here it is, the last piece of paper for this video, other than the answers, I guess. Although I think I'm going to do those out live. So, trying to frame this for you. Can you find the distance between A and B using our new distance formula? And can you find the distance between L and M using our new distance formula? So why don't you hit pause and try that. Alright, turns out I did set up an answer key, so let's see how you did. Can I get all this in one shot? That looks pretty good. So there they are. The distance from A to B, if I subtract the square root of, subtract my x's in square, plus subtract the y's in square, plus subtract the z's in square. So -3 minus 0 is -3, 0 minus -4 is 4, and 12 minus 0 is 12. Make sure you have the parentheses around any negative numbers there, because we want the entire number -3 to be squared, not just the 3. So we get the square root of 9 plus 16 plus 144. The square root of 169 is exactly 13. And on the other one, with the 2 points I gave you, it comes out to be the square root of 29. That's not a perfect square, so we'll leave that alone unless the instructions tell us to round off, but otherwise that's it. That's the exact answer. So now you have a midpoint formula in space and a distance formula in space. Good luck with the assignment.